Alright gang, here we go. This is for Chem 2 Unit 11. We're going to talk about polyprotic acids, do a little practice problem here towards the end. Should be a lot of fun. So essentially we're just building on what you already learned in the previous video about weak acids, being able to calculate concentrations of your hydronium and therefore be able to figure out your pH. And so polyprotic acids, poly means many, and protic is proton, right? So we're talking about many protoned acids. So these are acids that have more than one proton that can come off, all right? And so the way these work is with acids, it is always easier to remove that first proton than any of the successive protons. So, so like for like classic example here, sulfuric acid, H2SO4, that first proton to remove, that's a strong proton. That thing completely dissociates, and then you'd form the conjugate base, which would look, the bisulfate there. And so this second proton is a lot slower to come off. It's a lot harder to remove. And so this is a weak acid, all right, compared to the H2SO4, which is a strong acid. All right, now one cool trick we can use, all right, here it says if the factor of the Ka values for the first and second dissociation has a difference of 3 or greater, and really when we say that, we're talking about the exponents. All right, we're talking about the exponents here, so by difference we mean exponents are greater. The pH generally only depends on the first dissociation. All right, so if the Ka1 and Ka2 values, and those 1 and 2 refer to which proton's coming off, the first proton versus the second, then essentially we're just looking at, we can just look at the first one and ignore any of the rest of them. All right, so like for example, ascorbic acid is diprotic. There's 2 acidic hydrogens. That's what we put up in front. And so to take off the first one, the Ka value is 8.0 times 10 to the minus 5th. The Ka2 is 1.6 times 10 to the minus 12th. So these two have a 7 difference in their exponent values. So if we were calculating the Ka of this weak acid, we would really only care about the Ka1, the Ka2. The amount of hydronium formed by the second proton coming off would be so small it would be insignificant compared to the first amount. All right, so like the classic example here where you do have to worry about the second one is this guy right here, citric acid. You'll probably see this pop up more than once. Oxalic acid is another common one. This is the one we're going to look at later. And then let's see, what's the other super common one, or the other one here? Tartaric acid here is another one you kind of have to watch out for, although it's not as common as used of an acid as like citric acid is. All right, so we're going to walk through this problem here. So it says, and then we'll do a practice problem on our own. It says the solubility of CO2 in water at 25 degrees Celsius and 0.1 atmospheres is 0.0037 molarity. The common practice is to assume that all the dissolved CO2 is in the form of carbonic acid, which is produced in this reaction. And it says, what is the pH of 0.0037 molar solution of carbonic acid. So essentially all of this stuff doesn't really mean anything to us as far as answering the question. It's just kind of interesting. It's one of those, tricky. So when you're reading problems like this, make sure you don't get bogged down in stuff you don't need to know. All right, so it says, what is the pH of this? So we know that the first thing we need to do is come up with a balanced chemical equation. All right, so here they've come up with an analysis and a plan. All right, and so they were trying to find the pH, okay, and then carbonic acid diprotic, so we're going to have 2 Ka values, and so your 2 Ka values here, carbonic acid is 4.3 times 10 to the minus 7th and 4.6 times 10 to the minus 4th. All right, the pH can be determined by only doing Ka1 because they differ more than by a factor of 10 to the third. So really we can just use Ka1, and then at that point it essentially just becomes a weak acid, monoprotic weak acid problem. All right, so come on now. All right, so here's your balanced chemical equation. Get used to writing these like this. All right, where it turns into this, you'll also see them written as with a water thrown in there, so it'd be, and then this would be a hydronium. But so this is our initial concentration, and these are 0 to start with, and so we go down by a certain amount and up by a certain amount. It's all 1 to 1, so it's all of our x's are 1s, and so our equilibrium becomes this. All right, and then the equilibrium expression becomes this, and then we could solve this quadratic equation. Now we can't neglect this x like we have in previous problems because this is too close to our 10 to the negative 7th. This would be 10 to the 3.7 times 10 to the minus third, which isn't quite far enough to way to completely neglect it. So you'd solve that equation and you get your x value is this, and so we could take the pH of that would just be the negative log of that value there. All right. And we get, oh, and here they're showing you like that you could also have approximated this one, it's just the same thing. Anyway, so they get a negative log of 4.40. All right, so down here. Okay, now they're going to make a special case here. They're going to say if we were asked to calculate the concentration of carbonate, all right, we would need to use the Ka2, right? Because this would be formed because the first reaction would form our bicarbonate. We'd have that HCO3 minus, all right? And then when that guy undergoes an acidic reaction and loses that, it would form our H3O plus our carbonate. All right, so they said if we were asked to calculate that concentration of carbonate, we would have to use Ka2. And so they're going to illustrate that calculation. Now, one thing you got to be aware of, remember, is that first reaction, we actually already calculated the equilibrium concentration of bicarbonate and hydronium. All right, and so we get, oh my goodness. Okay, so this is our reaction that I wrote up here, right? This guy right here. And here's our ice table. Now notice that our initial concentration is that 4.0 times 10 to the minus fifth that we got before. And that's also the concentration of hydrogen, all right? But our initial concentration of carbonate is equal to 0 because we didn't have any of that from our previous reaction, all right? And then now they've used y's instead of x's just not to be confusing, or maybe it's more confusing, all right? And so you subtract x, all right, add x and y, or y's, whatever. And then now we know the reaction is going to go to the right. We could calculate our Q value. Remember, our Q is our reaction quotient. That tells us which way our equilibrium is going to go. But because this is a 0, we know that for sure it has to go to the right because the reaction to the left can't happen if there's no reactants to hit each other. All right. So our Ka2 value would be this. So we solve for our y value, and it says 5.6 times 10 to the minus 11th. Notice that this was 5.6 times 10 to the minus 11th. This would also be the concentration. This plus this would be the concentration of our hydronium. And so if we were going to add these values together, it would look something like 1, 2, 3, 4, and then a 4, and then we'd have 1, 2, 3, 4, 5, something like that. I think 56. So this would be the concentration, and you could easily see, well, this is friggin' like, 1, 2, 3, 4, 5, 6, 7, 8 sig figs. We don't have 8 sig figs in our problem. We only have 2. So it'd still be just 4.0 times 10 to the minus fifth. All right, so let's do a practice problem here. It says calculate the pH of a 0.2 molar solution of oxalic acid. And I already pulled out the Ka value, so we didn't have to skip through all that. So 5.9 times 10 to the minus second. And the Ka2 is 6.4 times 10 to the minus fifth. All right, so, and then it says calculate the concentration of oxalate. All right, so the first reaction here is when we go from oxalic acid to biaxylate, I guess. I don't know what it's called. It says C2O4, and that's going to combine with water, and we're going to get an equilibrium constant. Equilibrium H3O plus HC2O4 minus. All right, and we're going to set up our ice table. All right, our initial concentration of our oxalic acid was 0.020. All right, and then water doesn't participate in our equilibrium, so it's just going to be all dashes. Our hydronium is going to be 0 because we just started with pure water. Okay, so we're going to lose some amount of that. We're going to gain some amount of that. We're going to gain some amount of that. So this at equilibrium, this will be equal to 0.020 minus x, and then plus x plus x. All right, so our Ka1 is equal to 5.9 times 10 to the minus second. All right, and that is equal to x squared over 0.02 minus x. And you might be asking yourself, well, can we neglect this x? Can we ignore it? No, because if we did, this would be 2.0 times 10 to the minus first, and this is times 10 to the minus second. They're too close to neglect, so we actually have to solve the quadratic here. All right. So what I'm going to do, hopefully you know how to solve quadratic problems by now. So you just take this denominator, multiply it over, distribute it, and then subtract it over, and then set it equal to 0. So I'm just going to skip to the chase and just going to punch this guy into Wolfram alpha times 10 to the minus second. Okay, just to save us some time, and then also I'd look like a fool if I screwed up solving this on the video. Solving for these quadratic equations. Alright, so our x value, we got two x values. One is negative, one is positive. Obviously the negative value doesn't do anything for us, so that means we're just going to skip to the chase here. Our x value would have to be equal to 0.0158. Okay, so now we have to ask ourselves, well, does this run just for our pH value? Well, we have to compare these values here for our concentration, or our values of Ka1 and Ka2. This Ka1 is times 10 to the minus second. This is times 10 to the minus fifth. So according to our rules, we should be able to neglect however much hydronium is made from this. So we'll go ahead and do it here. So it would be the negative log of 0.0158. And then if we're feeling frisky at the end, we could go ahead and plug in whatever we get from the next part just to see if we get the same thing. So negative log of 0.0158. All right, and we get 1.80. So the pH of this guy here would be 1.80. All right, and remember this has 2 sig figs, and pH, this would have 2 sig figs because that first one before the decimal doesn't count. All right, so that's the first battle here. Okay, and then, but then it asks us for the concentration of the oxalate. I'm going to move myself up here so I got a little bit more whiteboard to work with here. All right, so second reaction here is when our conjugate base from the first reaction acts like an acid. So now our bioxalate, I guess I still don't know what that's called. What the short name would be. So, and then this is going to act like an acid to form our H3O plus and our oxalate. All right, we get another ice table. Now remember, the initial concentration now is going to be whatever our equilibrium concentration of the bioxalate was. So that's our X value, so that'd be 0.0158 here. All right, and the water still doesn't participate in our equilibrium. Our hydronium initial concentration is going to be what we calculated here as well, because these two things were made at the same time. All right, and then we're going to have 0 of this to start, which means we're going to lose some amount of this. So this will be 0.0158 minus y, and then plus y, and then this would be 0.0158 plus y, and then y. All right, so our Ka2 is equal to 6.4 times 10 to the minus fifth, and that's going to be equal to our reactants over our products. So this would be our products over reactants, so 0.0158 plus y times y over 0.0158 minus y. All right, now this guy, once again, we're kind of stuck. We can't really neglect this y just because of how close these guys are. We probably could, but since I have Wolfram alpha pulled up anyway, we'll just make him do the work, and then we don't make the mistake. Remember, one good trick is if you have a graphing calculator, you can just plug this into your graphing calculator and let it run for you. Equals 0.0158 plus x times x divided by 0.0158 minus x. All right, so we'll let it run. Kind of a tough one. Again, we have a negative x value and then a positive x value. That negative x value is not going to do anything for us. So this y, all right, so we're just going to skip to this. So the y is equal to, let's see, 6.335 times 10 to the, let's see, how many decimals? 1. Looks like 5. Let me count it again. 1, 2, 3, 4, 5. All right, yeah, 6.35 times 10 to the minus fifth. All right, so this would be the concentration of the oxalate. So the concentration of oxalate in our final solution here would be equal to 6.35 times 10 to the minus fifth. Alright, now just for grins and giggles, we could calculate the pH with this guy. So the pH of this would be the negative log of our concentration. So that would be a 0.0158 plus our answer, 6.35 times 10 to the minus fifth. And let's just see if we get a different answer here. So we could say negative log of 0.0158 plus 6.35 e to the negative fifth. And I get 1.7996. Alright, so 1.7996, 2 sig figs, we still get 1.80. So again, so our estimation, or our difference in our Ka was big enough that it didn't affect our pH, so we were right in our assumption that we could ignore it. Alright, so anyway, so these can be kind of confusing because you're running two ice tables in order to do one practice problem. You have to use answers from your previous problem in order to solve the next stuff. So it can be a little confusing to try to keep everything straight. The easiest way that I've found to do these is just try to stay as organized as possible while you're doing them. And then when you're doing them, just always make sure you do exactly the same steps in the same order, and that'll help you reduce making silly mistakes and kind of keeping track of what's going on. Alright, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.